So last time we had just started talking about slope fields, and we were starting number 32, and we were talking about how fields are an arrangement of information that just kind of exists, like a magnetic field tells a magnet how to act everywhere. But that magnetic field, that set of instructions exists even if the magnet's not there. And so that's kind of what we're trying to do with the slope field, is to figure out, to calculate, to write what the slope would be at every point, even if we don't necessarily want to put something there, even if it isn't necessarily something that we're measuring or directly observing at that point. So, in order to do number 32, we have a slope, dy dx, which is going to be 2x minus y. And we're told to draw tiny segments through the 12 lattice points shown in the graph and not to use your calculator. Okay? So over here, I'm going to put my graph. So I've got x and y, and I'm looking at points that are along x equals -1, x equals 0, and x equals +1, and then we're going from y equals -1 up to y equals 2. So I've got 12 points there, and we need to figure out how to draw in the slopes. So once again, I think it's really useful to make a table. And the thing that we're going to be filling into our table is dy dx. But I'm going to be filling it in for all my different x and y points. And this would probably be best if we let that be y equals 2, y equals 1, y equals 0, and y equals -1. Okay, and so we take each set of coordinates, x and y values, and we substitute it into our formula up here, and that gives us what our slope is. So for instance, if we took 0, 0, what are we going to get for dy dx? 0. Okay. If we took -1, 2, what would we get? No. -1, 2. So 2 times -1 is minus 2 is -4. Okay, so there are 10 of you. There should be 10 spots left. So everybody do one and fill it in. Ah, Casey. Okay. No, you just, when you picked it up, you hit the word thing. No, Priya. I do not have the energy to devote to that. I do not have the time to devote to you guys figuring that out. Okay. Did everybody do one? I think Sarah, yeah, I didn't think so. 2 years ago when I did this, I had just enough squares for everybody. And everybody swore that they had gone up and filled it in, and there was one left over. I erased it and made them do it again because I don't know why, but that's what we did. But like there were that many squares and that many people, and everybody said they filled one in. Like, but you didn't because there's a square left over. It's very annoying. And nobody would admit it. All right, so are we right? Okay, everybody's got the right side. I'm checking my stuff here. Wait a minute. I agree with that. I agree with that. I don't agree with that. Yeah, it should be 3. I used blue on purpose. Okay, so then you have to fill them in, okay, and draw them. So it's easiest to start with the zeros because you know what a slope of 0 looks like. Okay, so if we look at 0, 0, we're going to have a horizontal line. So we got that one. If we look at 1 comma positive 2, so that's going to be up here, that's going to be a horizontal line as well. So we got that one. Slopes of 1 are pretty easy too. All right, you're going to be comparing, these are kind of relative. So 1 comma 1 is the slope of positive 1. You know what that looks like. And 0 comma negative 1 is the slope of positive 1 too. Is positive 1 as well. So we got that one. Negative 1 you should have a pretty good feel for as well. So 0 comma 1 is negative 1. Oops. And negative 1 has a slope of negative 1. And then you just have to kind of be relative about it. So for instance, 1 comma 0 is going to have a slope of 2. Well, that needs to be steeper than your slope of 1. And 1 comma negative 1 has a slope of 3, and that's got to be even steeper. Negative 1 comma 0, that's negative 2, so that's not quite steep enough. That's got to be steeper than negative 1. Negative 1 comma 1 has a slope of negative 3, steeper still. And negative 1 comma 2 has a slope of negative 4, and that's got to be even steeper. So you have to do your best. They should be relative. We should be able to tell the difference between a slope of negative 4 and negative 1. You should. Oh, what's 0 comma 2? Negative 2. All right. So you want to make sure that that looks like the other places that have a slope of negative 2. Okay. You're not going to be perfect, but you need to do your best. Okay. And make sure that there is a relative difference between them. Well, again, it depends on what it is. It's the slope of the tangent to the curve at that point. But remember that whenever you have a differential equation like dy dx equals something, that it's a family of curves. So it's telling you that even though I don't know what your particular solution is, and you could actually kind of, these are tangents, so I could actually kind of trace these and somehow merge them together and draw my particular solution if I had a little more information. But it's giving me the tangent to the curve at each of those points. So it's giving me the rate of change for whatever y is. Y could be a velocity, y could be a position, y could be heartbeats, y could be water flowing over Niagara Falls, y could be anything. It's not necessarily a line. It's really going to be, if we solved this differential equation, which we could do. So this is dy dx is what, 2x minus y? Can I solve that? I don't even know if I can solve this off the top of my head. It's not a line, necessarily. Okay, it's not one. It's going to be something a little, probably more complicated than that. Well, remember in physics yesterday, well, I would solve for y. Remember in physics yesterday when we had, what did we have? Vrel dm was equal to, what was the other side of that equation? There was a dv in it, right? And something, maybe it was vrel over r was equal, you know, we integrated both sides of that equation. Yeah. And I ended up with v equals something. All right? We good? All right. Do we need to go over number 39 from the journal, which was match the differential equation? We didn't go over 39. We did the other graph ones. Yeah. Although, well, then let's do 39, because in 39 you can be a little clever. Okay, so somebody read us 39. Okay. And what's our differential equation for number 39? Okay, negative y over x. All right. So I have yet to figure out how to use the differential equation mode in your calculator, but we can do this by hand if we're creative. Okay. So the first thing to always look at are the easy things. So when y is equal to 0, what's dy dx going to be? 0, right? Does it matter what my x value is? No, as long as it's not 0 itself. Let me grab a book. Okay, so this tells us that all along what axis should we have a slope of 0? Where is y equal to 0 all the time? The x-axis, right? So that means we should have a slope equal to 0 along the x-axis. So if we look at our options over here in the bottom left-hand corner of the page, which one of those might be a good option? They look pretty vertical in A. So B and E look like, because the slope lines are kind of coming down like this, so along the axis they're kind of horizontal. All right. So B and E look like they fit this first observation we can make. Okay. Everybody looking at these graphs down here, right? Okay. All right. So that narrows it down. Now, we could pick out points and substitute things in and figure things out, or we could just kind of look at the different quadrants. So again, we have dy dx is negative y over x. So let's think about quadrant 1. So, sure. Okay. Yeah. We could say that because x can never be equal to 0, that it would have to be b. We're going to do it my way as well. But yes, that's a very good observation. Okay, so Zoe says then that it has to be b. So let's see if the way I would have looked at it, which is the way you may have to look at it in another circumstance, is going to back that up. Okay? So, quadrant 1. What do you know about x and y in quadrant 1? Yep, so they're both positive. Which tells you what about the slope? Really? It's going to be negative because x and y are both going to be positive, but there's that overall negative sign in front. So we're going to have a negative slope in quadrant 1. How about quadrant 2? Maggie, what can you tell me about x in quadrant 2? So x is going to be less than 0. And Sari, what about y in greater than 0? So Zoe L, what does that tell me about the slope? Yeah, it's going to be positive. Because even though my y values are positive, my x values will be negative, and that'll cancel that negative sign. Quadrant 3. Elf, what can you tell me about x in quadrant 3? Doesn't matter. Quadrant 3, x is always what? Okay. Priya, what can you tell me about y for quadrant 3? Yep. So Gianni, what does that tell me about dy dx, the slope? Correct. Because the negative sign from my y and the negative sign from my x will cancel, but I still have that overall negative sign in front. Quadrant 4. Rebecca, what can you tell me about x? Good. Sarah, what can you tell me about y? Zoe, what can you tell me about dy dx? Okay. So, if we kind of try to bring this all together then, we know that in quadrant 1 we have to have negative slopes. And so negative slopes are going to look like that. In quadrant 2 we have to have positive slopes, which look like that. Quadrant 3 we have negative slopes again. And quadrant 4 we're going to have positive slopes. So if we check back and look, that is consistent with B. Okay, and then you just kind of draw the little curve that follows the tangents, which is what all those little slopes are, and gets us through 0.3, 2. All right, we good? We got it? We feeling good? All right. One more big idea. Euler's method. That is how you say it. It's not like Euler, it's like Euler. As you would, but I have never heard it been anything other than Euler's method. Because it's... No. He's another dead white guy. What do you want? All right. So, Euler's method is a way to directly estimate the value of a particular solution without graphing the whole slope field. Okay? So, the best way, and you should have written down in your journal the steps for Euler's method, but the best way to show how it works is really to use it. So let's do page 331, number 51, if somebody would read it for us, please. 333, I'm sorry. I wrote it correctly. So that's all information that we need to have if we're going to do this. Now, as you can probably guess, I'm in heaven in this chapter because we get to make yet another table. And you know how much I appreciate a good table. Okay? So in the book, when we do this, we have some initial value of x and y that we're starting at. We figure out what the slope is going to be. You're always going to be given delta x. It's how much you move along the x-axis that'll help you figure out how much you're going to move along the y-axis. And the amount we move along the y-axis is the slope times how much we move in x, which kind of makes sense because the slope is delta y over delta x. And then we add our changes to our original point to get our new point that we then go and substitute back in for x and y and start the process all over again. So we want to get to x equals 1.3, but we only have information about x equals 1, y equals 2. But I want to know what y is when x equals 1.3. Okay? You with me? All right. So what's my slope going to be if x is equal to 1? 0. What's my delta x? What is it? 0.1. It's almost all, it's given. Sometimes they let you pick it, but it's given. And it will be the same for all of your values because you're just making these tiny little incremental steps. Okay. And then what's delta y going to be in this case? 0. So what's my new point going to be? 1.1 comma 2. It's y plus delta y. So it's 2 plus 0. Okay. And then that becomes my new starting point. So now my x value is equal to 1.1. So what's dy dx going to be? Not 1.1, 0.1. Okay. What's my delta x? Always 0.1. What's my delta y? Right? Because I'm multiplying these two together. And now what's my new point? I'm just adding my delta x to my x and my delta y to my y. It's a good thing. And then that becomes my new point. And so I'm just taking these tiny little steps to go from one place to another. So what's dy dx going to be now? 0.2. What's delta x? Because it doesn't change. Maggie, what's delta y? So Sari, what's my new point? Take x plus delta x, 3, because remember it was 1.2, and I add 0.1, and then what's my y going to be? Yeah, 2.03, good. And that's as far as I need to go, because I wanted to know what the y value was when x was equal to 1.3, and what's my answer? Yeah. And this was moving towards the right, towards more positive values of x, or larger values of x. I could move the other direction if I was still starting at 1 comma 2, but I wanted to know what the value for y was when x was 0.5. I would just make my delta x negative. That's okay, and it'll shift it in the opposite direction towards more negative numbers. Okay, and again, if you respect the negative signs, the delta y will work itself out and you should get to where you want to be. And you need to remember that a lot of these methods, this method, Newton's method, were created before we had calculators to do calculus with, when we had to do everything by hand, when we had to approximate everything by hand. Okay. All right, I think we have time for number 62. which again might have been a journal question. Was it? No? Okay. Well, why doesn't somebody read us number 62 then? Sure, it's right around page 333. Bless you. Okay. So, what's plotted in a slope field? Not the slope of the derivative. Yes, which is the derivative. Okay, so remember the derivative is the slope of the tangent. So if you take the slope of the derivative, that may be the second derivative, which is not what we want. Okay, so write down an answer. Actually write down an answer. Think about it and think about why that would not work. They show what? Correct. That's why, because the slope of the derivative would be the second derivative, which isn't what we want. A slope field is the tangent or the slope of the function. All right, so dy dx, you should have figured out was cosine x, right? So when you got a trig function, we usually think about, 0, pi over 2, pi, is those lines there. So for instance, what is the cosine of 0? So if I evaluate that at x equals 0, I should have a slope of 1 going up and down the y-axis. Do I have that? No. Okay. So I'm not even going to write it down because you already wrote it down. All right. So tomorrow is the test. If you turned in homework, I graded your homework. If you did not turn in homework. If you turned in your homework, I graded your homework. The test is tomorrow. We will start 7.2 on Monday. Okay? Have a lovely day.